Hi guys, so this is part 2 of chapter 12, and that's our acids and base chapter. So in this section, we're going to go over the different types of chemical reactions involving and acids and bases. So the first one is going to be an acid-base neutralization reaction. The second one is reactions of acids with metals. And the third is the formation of acids from non-metal oxides. So we'll cover all of those little by little. So in this first one, we have the acid-base neutralization reaction, and that's quite simple. That basically says if we have an acid plus a base, you're going to produce water and a salt all the time. You'll always produce this. So what is a salt? A salt is basically a metal with a non-metal combined together. Sodium chloride is the most common form of salt. It's actually table salt, very specifically. But there's also magnesium chloride, potassium chloride, potassium iodide, all these different ones that are considered salts. Water we know as H2O. So in an acid-base neutralization, okay, you're going to have your acid. So in this case, let's have our hydrofluoric acid and our base, which in this one is sodium hydroxide. If we recall from the last section, an acid always has the hydrogen before the halide or halogen, and the base is always going to have the hydroxide at the end of it. So these ones react together, and when they react together, in this reaction, you're going to have the hydrogen go with the OH and the sodium combine with the fluorine. Okay. So it's a double replacement reaction. Double replacement reaction. So our H2O gets formed, our water gets formed, and then our salt, in this case, our salt is just sodium chloride. So this is a double replacement reaction, or a type of double replacement reactions that we've seen before. This would be just another example showing it with a polyatomic ion, right? So this chlorate molecule that we have here is a polyatomic ion. So we have hydrogen and chlorate added together, so we have an acid. And in this acid, the same thing's going to happen. The hydrogen leaves and combines with the hydroxide because acids are hydrogen donating. They donate their hydrogens, okay? Or produce hydrogens, depending on which definition you're using. So these donate the hydrogens, and the bases accept those hydrogens. So hydrogen combines with our hydroxide to form water. The potassium then combines with the polyatomic ion of chlorate, and then we get potassium chlorate. So now let's break this down into the different sections, similar to what we're used to looking at. We have the molecular equations, and then we're going to go over the complete ionic. Now, the reason we're able to do this is because not everything is aqueous. We produced a liquid. So you know that you're going to have one of these reactions where you could have a complete and net ionic reaction when you produce a liquid, a gas, or a solid. Right? So liquid, gas, or solid in your double replacement reaction. If they were all aqueous, then you have no reaction. All right, so let's go over this first one. This one is going to be our molecular equation. Okay. Molecular equation. And in the molecular equation, hydrogen and chlorate. I'm going to use the different colors to represent it just to make it easier for us to see. This is aqueous, okay, dissolved in water, plus my potassium hydroxide. check there. And this one is also aqueous. Now, they're going to combine in a double replacement reaction to form water. Right? So this hydrogen and that hydroxide are going to join together, and we're going to get H2O plus our salt. And our salt is potassium chlorate. Water is a pure substance. And because it is a pure substance, it is a liquid. Okay, so it's a liquid. Now the complete ionic equation, we're just going to break everything apart, right, into its ionic form. I'm going to use a pen this time to write it a little bit smaller. So our hydrochloric is going to break up, hydrogen being positive, and our chlorate having a -1 charge is aqueous, plus our potassium with a +1, plus our hydroxide with a -1, and these are all aqueous. You notice I put them all together, just one little thing. I don't even separate them. And they're going to form H2O. Note that the H2O is a liquid, so it stays together. It does not dissociate in this reaction. However, our salt is aqueous, and our salt does dissociate in this reaction. Okay, so we went from molecular, and now this one is going to be our complete ionic. Reaction. And now we're going to write our net ionic reaction. And if we recall, in the net ionic reaction, we're going to get rid of everything that is not part of the formation of our liquid. So our liquid was made of our hydrogen and our hydroxide. That means everything else is called a spectator ion. So in our net, we're going to have our hydrogen, aqueous, plus our hydroxide, aqueous, join together to produce our H2O liquid in our reaction. We could write what our spectator ions are just in case you ever get asked, well, what are the spectator ions? Spectator ions. Well, those are the ions that had nothing to do in the reaction. They didn't help, not one bit. So we have our chlorate, the -1, aqueous, plus we had our potassium, aqueous. Those were our spectator ions, and they are present on both sides. Okay, so here and here. You don't have to write your spectator ions down as an equation format. They cancel each other out, basically. Okay. The thing to note about this is that the formation of our water, this one right here, that's what actually drives the neutralization process. So water formation drives the neutralization process. That means it allows it to go forward, okay? It allows it to proceed. Now we have a practice problem. Write a balanced equation to show the reaction of aqueous nitric acid with aqueous calcium hydroxide being formed together. Right. So let's write actually the problem. This is an example. So we want to write a balanced equation showing reaction of nitric acid, aqueous, and calcium hydroxide, aqueous. Okay. I just have those formulas kind of memorized. You could always figure them out. Figuring out what is nitric acid, Google it. But that's HNO3. And our calcium hydroxide, we know what hydroxide is OH with the -1 charge. Calcium is just our metal from the periodic table, right? Elemental right there. And it has a +2 charge. So therefore, you're going to need 2 hydroxides for every 1 calcium when they're formed together. Let's go ahead and write down our balanced equation showing this reaction. So we're going to have HNO3 aqueous plus calcium hydroxide aqueous. Well, what are these going to form? We have just been talking about this being similar to a double replacement reaction, and we're going to produce a water and a salt. So no matter what, we know we're going to produce H2O plus a salt. And let's figure out what that salt is going to be. So the first thing is hydrogen is going to combine with hydroxide. Calcium is going to combine with my nitrate. So I'm going to have calcium, always write the metal first, and then my nitrate group. And then I have to make sure I balance these out. Okay, so HNO3, nitric acid. You know what? I'm going to double check that it's HNO3 and not H2NO3. Nitric acid. Sometimes, okay, I'm right. HNO3, we're good. Okay. Sometimes I mess up, as you guys have seen. So these combine together. Nitric acid, or NO3, has a -1 charge to it. I know this because hydrogen has a +1 and it combines in a 1:1 ratio. So therefore, I'm going to need 2 of those to balance out the 1 calcium. Right? And now I have calcium nitrate. And now I'm going to balance out everything else that I have. So I have 2 nitrates, therefore here I am going to actually need 2 HNO3. So now I have 2 nitrates on this side, 2 NO3s, 2 NO3s here. I have 2 hydrogens here, and I have 2 hydrogens there. 1 calcium and 1 calcium, and therefore my equation is now balanced. Hey guys, okay, so the equation's not balanced. I was actually a bit distracted. I had a phone call that came through. So actually, let's finish balancing this equation right here. So we have 2 hydrogens here, 2 hydrogens there. That looks like it's balanced. Yet, we have more hydrogens. We also have these 2 hydrogens right there. So we have a total of 4 hydrogens that we have to balance out. Super easy for us to do that. And that's also going to balance out our oxygens. We're going to add a number 2 right there. So now we're going to have 4 hydrogens and 2 oxygens on this side. We're going to have 2 hydrogens here and 2 hydrogens there, which gives us a total of 4 hydrogens. So our hydrogens are balanced. Our oxygens, 2 oxygens here, 2 oxygens there. Oxygens are balanced. We have 2 nitrics here, and we have 2 nitrics on the other side, the product side. The nitrics are balanced. And the last but not least, the calcium, 1 calcium here and 1 calcium there. Our calciums are also balanced. So I'm just going to put a 1 and a 1. And now our equation is completely balanced. This is a liquid, so I'm going to put the state of matter there, and this one is aqueous. Also going to write that state of matter there. Let's see how we did. All right, so far we've written the equation correctly, and we balanced it correctly as well. So that's what we want. We also noticed that they also wrote aqueous and liquid, so they indicated the states of matter. You have to indicate the states of matter when writing a chemical equation. All right, so now we're on the second one. We just did acid-base neutralization, so now we're going to do reactions of acids with metals. That's the next spot. So number 2, reactions of acids with metals. So in this one, usually it's going to be a single replacement kind of reaction. So you're going to have your metal and you're going to try to place it inside an acid, and we're going to see if the equation goes or does not go. Right? So this is more like a single replacement reaction. Now, in the example that we have iron metal, and iron metal is trying to react with hydrochloric acid. And we want to see if a reaction gets produced or not produced. You see that a reaction does get produced by the evolution of gas. So we have hydrogen gas that is actually being produced. That's because the acid produces hydrogen. The acid produces hydrogen. So I'm going to look at the activity series with hydrogen so that we could see it, what reacts and what doesn't react. Activity series with hydrogen. Right, now I wasn't able to find exactly what I wanted to show you guys, but however, if we look at this activity series, we could get a little bit more of an understanding of the reactions that we're going to see here. So if you can see hydrogen here and all of these metals up here. So hydrogen will most likely, hydrogen from the acid, hydrogen that gets released from the acid, will react with these metals, right? And it's less likely to be reacting with these ones right here. All right, so let's go ahead and continue reactions of acids with metals in this single replacement reaction. Okay, remember that's like our home wrecker kind of reaction. Okay, so the same thing is going to occur that occurred in the other ones. We're going to have our molecular equation. Okay, and that's going to show everything. Okay, it's going to show everything. So in my molecular equation, this is my example of my metal plus my acid. So iron is my metal, and my metal, it comes in a solid form. Plus my acid, hydrochloric acid, and that is going to be aqueous. There is 2 of those, so they already balanced it for us. And that's going to produce 1 iron chloride, aqueous, plus hydrogen gas. Okay. Now, if we look for the net ionic equation and we try to get rid of any spectator ions, well, that's going to be a little bit hard. And let's just actually not hard. I don't know why I said that. It's actually quite easy. Let's go ahead and separate everything. It's easier than the other one. Okay, iron is a solid. So guess what? It's going to stay as iron solid. It does not dissociate. Hydrochloric acid does dissociate. We have 2 of these, so I'm going to have 2 hydrogen ions and 2 chlorine ions, both aqueous. And that's going to produce my iron chloride, which is also aqueous. And there's 2 chlorines. They're also aqueous. Plus my hydrogen gas. Okay. And we're going to get rid of anything that wasn't involved in the creation of our hydrogen gas that can be gotten rid of. So if you have a solid, you can't get rid of your solids. So the best way to think about this is anything that repeats itself on the other side, you're going to get rid of. Iron solid does not repeat itself because it turns into aqueous, so we can't get rid of that. Hydrogen aqueous, hydrogen gas, we can't get rid of that. Chlorine aqueous, 2 on both sides, we're going to get rid of those ones right there. Those are spectator ions. And now we're going to go ahead and write our net ionic equation. That's going to be our iron solid plus our hydrogen aqueous, producing our iron aqueous, or our iron ion, and our hydrogen gas. Right. So most of our metals will react with our hydrogen gas. As you guys saw in the activity series, there's other metals like super heavy metals that don't react with normal acids, right? They're going to need something else. So like platinum, gold, you could throw them in regular hydrochloric acid and they won't dissolve. You're going to actually have to make something like aqua regina, which is a mixture of acids, to actually be able to dissolve those high metals. So platinum, gold, silver, okay? All of these ones right here, you're going to need something called like aqua regina for that. All right, let's go ahead and look at this one right here. We have tin and nitric acid. In the reaction of tin and nitric acid, we produce tin nitrate and hydrogen gas. Single replacement reaction, just like on the other ones. Tin reacts. It's also above it on the activity series. You can see here's tin. It's above hydrogen on the activity series. It's going to react with it. Okay. The net ionic equation, you get rid of anything that wasn't part of the formation of your hydrogen or isn't in your solid either. Nitric repeats itself on both sides. If you were to draw the complete ionic equation, this is the complete ionic, then you would see that nitric, you could get rid of it. So this is our complete ionic equation right there. Right. The precious metals are our heavy metals, the ones that I keep mentioning that you're going to need aqua regina for. So like gold, silver, and those kind of metals right there. Platinum, you're not going to react them with your normal acids. All right, now we're on part 3. And part 3 is the formation of acids from non-metal oxides. Non-metal oxides. So non-metals, oxides basically means what you hear. It's not a metal and it's connected to oxygen. Oxides basically just means oxygen. And they often react with water to form acids. So let's write what our oxides are. Okay, so in the formation of our acids, I went ahead and I listed a couple of examples of what it means to be a non-metal oxide. So like carbon monoxide, carbon dioxide, our nitric acid, our sulfate. These are all non-metal oxides, right? It's a non-metal covalently bonded with an oxygen. Okay. Now, what we notice in these is that at times when they bond together, they are going to form some sort of carbonic acid. So in this case, CO2 is forming carbonic acid. Let's take a look at the other ones, right? We have our SO3. SO3 combines together to form our sulfuric acid. Our nitrogen oxides, they combine together to form nitric acid, right? So all of these is we're producing acids from something that wasn't, okay? Producing acids from something that wasn't. So in our first example, we had CO2. Let's go back to it. And CO2 produced carbonic acid. Right? And it reacts with water to do that. Then the next one, we had our sulfur oxide, so an SOX, and that one produces sulfuric acid. Now there's sulfurous as well. It all depends on how many oxygens you have. Our NO3 or NO groups. So I'm just going to write NOx as well. Okay. So the X just means any number can go there, any number of oxygens. They react with the water to produce our nitric acid. Okay, so all of these are reacting with H2O. They're all reacting with water to produce that acid. The example that you guys see right here is a statue, and in this statue, that's actually not even the right color. What ended up happening is over the years, acid rain. Okay, so acid rain is a combination of pollutants mixed with H2O, creating some sort of acid like sulfuric acid, and that ends up dissolving our metals, rusting them, one might say. So sulfuric acid and nitric acid, right, form from the byproducts of burning coal and oil. So SOX and NOx, right, those are formed, and then those create the acid when they're mixed with our rainwater. That's why it's actually very important to know what kind of factories you have around you. Where does the wind go from your area? So it might be that you guys have a oil burning factory next to you, and it doesn't affect you. You don't know why. Well, maybe you're on top of a mountain and the wind blows down. So everyone in the valley actually gets affected by the byproducts and suffers from acid rain. Um, so these are things to think about when making decisions in your community. All right, so we're going to talk about acid-base concentrations now. What it means to have an acid-base concentrations now that we've gone through these different formations. Okay, so we know that not all acids are as strong as the other acids, right? Same thing with the base. They all vary in acidity, right? We could eat chicken wings, which are acidic to us, but we can't drink hydrochloric acid. So starting off with self-ionization of water, we noted in the last video that water can be both an acid and a base, and that's because water self-ionizes. I'm going to put that down, and I'm going to a little section here. We're going to call it concentrations of acids and bases. So concentrations, this little bracket equals concentration. And the concentrations are going to vary. They're going to change. We note that water can self-ionize. Okay, so that just means it can break apart to produce hydrogens and hydroxides. H2, a liquid, can be both an acid and a base. So the reason we bring that up is because in this self-ionization, when you combine them together, you're going to have equal amounts of concentration of your hydrogen and your hydroxide if you have pure water. So the concentration of our hydrogen and the concentration of our hydroxide are going to produce 1 times 10 to the negative 14 of concentrations, molecules ionized, right? Um, what that means is that these could actually be separated, right, to give us this quantity here. See if it shows us this. Not yet. Okay. So I'm going to go ahead and show you what I mean. Okay. Right here, that's a negative. Okay. So the hydrogen and hydroxide would equal 1 times 10 to the negative 14th. Okay. Now let's go ahead and talk about our concentrations. As we add acid, your hydrogen concentration goes up and your hydroxide concentration goes down. As you add a base, the opposite's going to happen. Your hydrogen concentration is going to go down and your hydroxide is going to go up. So let's write that down. Okay, acid and base. So I went ahead and started that. So as you add acid, hydrogen goes up and your base actually goes down. As you add base, the base goes up, but the hydrogen goes down. Right. So this is a quick little math review to help explain exponentials. Right. So we have standard notation, scientific notation, and we actually have exponential notation, which are very similar to each other. We can convert from one another or show our numbers in different ways. Now, we use scientific notation because numbers can be extremely small or extremely big, and it's really hard for us to mentally actually process huge numbers or work with them. So that's where scientific notation and exponential notation actually come in hand. Now, for scientific notation, the first couple of numbers are coefficients. The power is considered our integer, which is our exponent, and our multiplier is 10. So that means that the coefficient 2.14 gets multiplied by 10 negative 3 times, which actually means divided by, if you have that negative because it's a smaller number. And in exponential notation, this is our base. Your base could change. However, we're going to stick with the base 10, okay? And that just means 10 to the negative 2.67, which is a little bit different. So our exponent, not an integer. An integer is basically a whole number. Okay. In this case, in exponential notation, it does not have to be a whole number. All right. To review some more of the mathematics, I believe I showed this to you guys in a different video as well. You have x to the m and x to the n. This is exponential notations. That's the same as saying x to the m plus n. You add them together. If you look at this example here, negative 7 plus negative 7 is equal to negative 14. The next example that they give you is 5 to the 2 and 5 to the 7th. Well, that's just going to be 5 to the 9th. You just add them together. They're not showing you this other one, but I'm going to go ahead and show it to you. It's when you divide them. Okay, so you could have x to the m divided by x to the n, and that's going to equal to x to the m minus n. You just subtract them. They have to have the same base, so they must have the same base. And then in this case, it's the base of 10. So just consider that you must have the same base. Okay, or multiplier per se, right? Right. Now let's go ahead and start looking at these concentrations. Okay. So in the concentration of hydrogen ions, this is the amount of moles per liter. Okay. If you're an acid, you're going to have 1 times 10 to the 0. Okay. Basically 1 mole per liter is going to be considered extremely acidic. And as you go down, you notice that your hydrogen ions also go down. 1 times 10 to the negative 14th, right? That's 0.000000000. Like there's 13 zeros and then the 1. That's very, very small amount of hydrogen ions when you are basic. Okay. So 1 times 10 to the 0, even though it might seem like a small number to us, it's actually big if you compare it to the rest of the numbers in our chart. The hydroxide concentration is just the opposite of that, just the opposite. If you're told you have an OH with a value of 10 to the negative 14, this is an OH. Well, it's the opposite of your H, of your hydrogen, right? So therefore, this is going to be very acidic. If you're told you have a hydroxide concentration of 1 times 10 to the 0, well, your hydroxide concentration, remember, opposite of the hydrogen concentration. So 1 times 10 to the 0 hydroxides, it's actually very basic. Right. Let's look at this example. The concentration of hydrogens in an aqueous solution is 1 times 10 to the negative 6. What is the concentration of hydroxide? Is this solution acidic or basic? So let's go ahead and put our example down. Okay. We are given this. We are given 1.0 times 10 to the negative 6 molar. Of what, though? The concentration of hydrogen ions of this right here. And we want to know, is this acidic or is this basic? Okay. Well, neutral is equal to 1 times 10 to the negative 7. That's going to be neutral. And as you go down in hydrogen concentrations, you become more basic. So as you go down this number, you become more basic. So therefore, this number must be acidic. So we have an acid. The next question is, what is the concentration of hydroxide in this? Well, if we recall to negative 6, we take this concentration and multiply it with the hydroxide concentration. We should get this right here. Now we want to isolate X, so I'm going to go ahead and divide both sides by this number. That cancels out. We're left with X is equal to this right here. Now, I just showed you guys up here how to solve these problems that have the same base slash power multiplier. So this is going to be 1 times 10 to the negative 14 minus negative 6. X is going to equal to 1 times 10 to the negative 8. Okay. So hopefully I did that math correctly. And this would be the hydroxide concentration, the OH concentration. Okay. Let's see how we did. Okay. Well, we have our equation. We put things together. We solve the problem. We get to negative 8. Oh, I forgot my unit. Molar, moles per liter, right? The concentrations that were given to us are in moles per liter, molarity. They're just very, very small numbers of molarity. All right. Quite simple, right? Okay. Now we're going to go into something else, the pH scale. The pH scale is the one that we're used to dealing with. The pH scale is super easy because it just goes from 1 through 14, and we don't have to worry about this kind of mathematics. However, if we know the hydrogen concentration or hydroxide concentration, we could figure out the pH value, and we could figure out the pH value, we could figure out the hydrogen concentration or the hydroxide concentration if we know the pH values. It all just kind of sticks together and works together. All right, so pH is equal to the parts of hydrogen is equal to the negative log of our hydrogen concentration. Okay, the negative log of our hydrogen concentration. So if we have 1 times 10 to the 18th, then the log is going to be 18th. If we have 1 times 10 to the negative 2.3, the log is going to be negative 2.3. And if we have 100, which is the same as 10 to the second, the log, as you guessed, is going to be 2. Now, I'm keep saying the log because we're talking about the log, not the pH. So now let's look at if we have hydrogen concentration and what the negative log of that hydrogen concentration is going to be. So 10 to the negative 7, well, we're taking the negative log of that, and that's just going to be 7. 10 to the negative 13, take the negative log, 13. 10 to the negative 5.8, you just get 5.8. Now remember, these are all 1 times 10 to the negative 7, right? This right here is only working because it's a 1 times 10 to whatever power, right? Let's go ahead and take a look at this. Like how are we actually using this? So in a strong acid, if you have 1 times 10 to the 0, your pH is 0. If you have 1 times 10 to the negative 5, your pH is 5. Your pH will match whatever the integer is up here. If it's a 1 times 10 to that number. The moment this number 1 changes, then you're going to actually have to start some mathematics, right? This little shortcut doesn't work anymore. The POH, or parts of hydroxide, is the same as the pH and number, and then the HOH, right, equation. So I'm not writing these down because I'm going to write it down in a different way for you guys to be able to see it and actually work better with it. And so we're going to go ahead now and write those equations and then work some examples out with them. So I'm using different colors to represent my my hydrogens and my hydroxides. If you guys want to do the same thing in creating your chart, I highly recommend it. Okay, so before I start writing everything, I'm going to write all the equations. I'm going to write the parts that I'm looking for. So in this case, the hydrogen concentration and the hydroxide concentration. And then we're also going to have the parts of hydroxide and the parts of hydrogen. So at any given point, we would have to calculate for one of these 4 parts. Now, let's connect them together. So to go from the hydrogen concentration to the hydroxide concentration, remember there's that one equation that puts them together, right? And that is going to be 1 times 10 to the negative 14th is equal to your hydrogen concentration and your hydroxide concentration. So you're going to use that equation to solve between any one of that you might need. Okay. What about from OH to POH? Okay. So to go from OH to POH, let's write this one down. POH is equal to the negative log of hydroxide. What if we wanted to go the opposite way? So if we had parts of hydroxide and we want the concentration of hydroxide. Well, I'm going to just twist this really quick just so I can write a little bit better. Our concentration of hydroxide is therefore going to equal to 10 to the negative pH. I'm not quite sure if that's the inverse log, if that's what we call it. If you're taking a math class, ask your math instructor, see what they say, and then let me know. All right, so now we're going to go from parts of hydroxide to parts of hydrogen. And that equation is probably the easiest of them all because parts of hydroxide plus parts of hydrogen equal to 14. So therefore, you could use this equation to go both ways. Okay, to go both ways. Right? Well, if I want to find hydrogen from parts of hydrogen, then let's do it this way. My hydrogen concentration is going to equal to 10 to the negative pH. And this is POH right here. Let's fix this equation. Parts of hydroxide. And then if I wanted to go from hydrogen to this one, to parts of hydrogen, well, that's going to be pH is equal to the negative log of my hydrogen concentration. All right, so now we have all our equations written down, and we have them in a way where we could actually go from one to the other. I can go from here to here to here to here and just follow the steps and vice versa. Okay? So very, very, very useful chart. All right, let's do an example and hopefully we can use our chart. A chemist measures the acidity of a solution and finds that the hydrogen concentration, so our hydrogen concentration, is equal to 0.01 molar. What is the pH of the solution? Is the solution acidic or basic? So we have this hydrogen concentration, and I want to know what the pH is. I want to know what this one is. So the equation is pH is equal to the negative log of H. My hydrogen concentration. So pH, and this should actually be lowercase p, not capital P, is equal to the negative log of the concentration given to me, 0.01 molar. And all I have to do is put it in my fancy dancy calculator. Now I know there's like a step for this that we could easily do it in our head. However, I rather do it in my fancy dancy calculator. So I am looking for the negative sign. Oops. The negative sign. And now I'm looking for log on my calculator. Log of 0.01. And I get 2. pH is equal to 2. Okay? That works. So this right here, 0.01, is equal to 1 times 10 to the negative 2. And if you guys remember, if you have a 1, this is the shortcut. If you have a 1, then your pH is whatever power is going to be here. In that case, it's going to be 2. All right. And because our pH is 2, this is going to be acidic. Oh, well, there you go. It explained it to us. So scientific notation, we get 1 times 10 to the negative 2. Exponential is just going to be 10 to the negative 2. So therefore, we could easily interpret and say our log is going to be 2. And it's acidic. Right? But if you can't remember that trick, I don't remember it all the times, put it in your calculator and you're going to be just fine. All right. A solution of hydrochloric acid in water is found to have a hydrogen concentration of 0.0030 molar. What is the pH of this solution? Okay. So 0.0030. Let's look at this other example. A hydrogen concentration is equal to 0.0030 molar. Now, this is the same as 1 times 10 to the negative 3. It is the same as 1 times 10 to the negative 3. And if we write that down, we're going to get a pH equal to 3, which means it is acidic, right? Oh, what did I do wrong? Did you guys catch it? I caught it. This is wrong. So therefore, that's wrong as well. All right, why is this wrong? Did you guys know why it's wrong? Correct. So we're going to go 1, 2, 3, and the decimal goes there. And this is going to be 3.0. What is that? 1, 2. Just 3.0 is going to be our number times 10 to the negative 3. All right. So our pH is close to 3, but it's not going to be 3. And the reason why is because this is not a 1 right here. This is a 3 now. So what you do in these cases is you just estimate what your pH is going to be. So you could say your pH is about, let's say you didn't have a calculator, right? You don't have one. It's about maybe 2.2 or 2.5 maybe, whichever one you think it's going to be. Okay, so if we actually take the log of it, we get 2.5. And let's go ahead and do that in our trusty calculator and see how it's done there. So we have the negative log, and we're going to put in our number of 0.003. And we get 2.5228, which is going to be 2.5 as our pH. And this is going to be acidic. Right? Another example, carbonated soft drinks are fairly acidic and typically have a pH of about 3. What are the hydrogen and hydroxide concentrations at this pH? Let's just quickly go over it. So it has a pH of about 3, right? So the pH is equal to the negative log of hydrogen concentrations. So the hydrogen concentration is equal to 10 times the negative pH. Okay? And 10 to the negative 3 is the same as saying 0.001 molar. So if we put it into our calculations, right, and try to figure out, well, what is going to be the hydroxide concentration from this, we could say that the hydroxide concentration is 10 to the negative 14 over 10 to the negative 3. That's the same as 14 minus 3, which is going to be negative 11 in this case. So we're easily able to solve both of them. The first one, we're given pH and we want hydroxide. So we take the inverse log of 10 to the negative pH. See, I'm going to try to find it on my calculator and quickly go over it using my calculator. All right. So my calculator has it where the log is the 10 to the x button right there, or a little square. So I'm just going to click second, shift, get to that thing, and it's going to be 0.001, or a pH of 3 basically, negative 3. And I get 1 times 10 to the negative third. So this is now my hydroxide concentration right here. And from that, I could find what my OH is by plugging that into here. And you just divide this by that number, which gives you the negative 11. Right. Oh, and it has to find the pHs as well. So the pH of our first concentration is just going to be 3. And therefore, if you take 14 minus 3, you get 11. So the POH is going to be 11. Let's look at this equation. What is the hydrogen in an aqueous solution of a pH of 9.43? So now we could actually plug that into the same calculation that we did right up here. Right? So I'm going to go second, shift, and I'm going to put negative 9.43. Okay, and we get this beautiful number, okay, of 3.72 times 10 to the negative 10 molar. And this is our exponential notation, scientific notation. All right, that's it for that part right there. We're going to go into another section, which is called measuring acid and base concentration. So hold on for part 3.